Today we discuss what is an abrupt PN junction. The constant Fermi level required at the thermal equilibrium results in a unique space charge distribution at the junction. The one-dimensional PN junction and the corresponding equilibrium energy band diagram are shown over here in this diagram. The unique space charge distribution and the electrostatic potential are given by Poisson's equation as we have discussed previously. This is the example of abrupt PN junction. So, to solve the Poisson's equation, we must know what is the impurity distribution. So, we will be considering two important cases, the abrupt PN junction and the linearly graded junction. So, here we have an abrupt junction, that is, a PN junction is formed by shallow diffusion or low energy ion implantation. The impurity distribution of the junction can be approximated by an abrupt transition of doping concentration between N and P type regions. Here we have an abrupt junction. We will be afterwards in our next lecture discussing what is a linearly graded junction. So, now we will start with what is an abrupt junction. The space charge distribution of an abrupt junction is shown over here in this diagram. In the depletion region, free carriers are totally depleted, so we can write the Poisson's equation as d square psi by dx square is equal to qNA by epsilon s for the region x lying between minus xp and 0. So, this is how we define an abrupt junction. So, this equation will simplify to d square psi by dx square, this is equal to minus q nd by epsilon s for x lying between x and xn, x lying between 0 and xn as we have discussed over here. So, the overall space charge neutrality of the semiconductor requires that the total negative space charge per unit area in the p side must precisely equal the total positive space charge per unit area in the n side. So, we have NAXP is equal to NDXN. The total depletion layer width W is given by XP plus XN. The total depletion layer width W, so now becomes W is equal to XP plus XN. The electric field will be given by minus d psi by dx, this is equal to QNA in brackets x plus XP bracket close divided by epsilon s for x lying between minus xp and 0. For the electric field epsilon x, this is equal to minus epsilon n plus q nd x by epsilon x. This is equal to q nd by epsilon s in brackets x minus xn. This is for x lying between 0 and xn, where xm is the maximum field that exists at x is equal to 0 and is given by epsilon m, or the electric field, the maximum electric field is given by q nd xn divided by epsilon s, that is equal to q na xp by epsilon s. So, if we integrate this equation over the depletion region, this gives us the total potential variation, that is the built-in potential VBI, and that value is given by integral of Ex dx. So, this becomes in the limits of minus xp and xn, that is equal to minus xp in the regions of xp and 0. If we integrate this in the p side and xn and 0 in the n side. So, what we have finally is VBI is equal to minus integral of E dx in the limits minus xp to xn. So, this can be divided into two parts, that is minus E dx in the limits of minus xp and 0 in the p side minus 0 and xn E dx on the n side. So, this becomes equal to QNA xp square by 2 epsilon s plus QND xn square by 2 epsilon s, that is equal to half EMW. Therefore, the area of the field triangle corresponds to the built-in potential. So, if we combine, we will get the total depletion layer width as a function of built-in potential. So, that built-in potential W, that can be given as the total depletion layer width, that can be given as under root of 2 epsilon s by q Na plus Nd divided by Na Nd into Vbi, as you have shown in this equation over here. When the impurity concentration on one side of the abrupt junction is much higher than that on the other side, the junction is called the one-sided abrupt junction. The space charge distribution of a one-sided abrupt PN junction, where Na is very much greater than Nd, in this case, the depletion layer width of the P side is much smaller than the N side, and the expression for the depletion layer width W can be written as W is equal to Xn, and that is equal to under root of 2 epsilon s Vbi divided by Qnd, as you have shown over here. The expression for the electric field distribution can be written as Ex is equal to minus Em plus Qnbx divided by epsilon s. Here the Nb is the lightly doped bulk concentration, that is Nd for P plus N junction. The field decreases to 0 at x is equal to W, that is Em is equal to Qnbw divided by epsilon s. And so the electric field will now become equal to Ex is equal to Qnb divided by epsilon s in brackets minus W plus x, this is equal to bracket close, this is equal to Em 1 minus x by W. If we integrate this, the equation once more, we get the potential distribution psi x is equal to minus in the limits of 0 and x E dx, so that becomes equal to Em x minus x square by 2W plus constant. So this with 0 potential in the neutral P region as a reference, or psi 0 is equal to 0, and employing the previous equation, we have psi x is equal to Vbi x divided by W, 2 minus x by W, and this we get the potential distribution over here, that is psi x is equal to Vbi x divided by W, 2 minus x by W. So here we have discussed the abrupt PN junction. In the one side abrupt PN junction, the depletion layer width of P side is much smaller than the N side. This is all that we have for